Hello again. We've been talking a lot about convergence and divergence of sequences and series and integrals. I want to talk about what tests you can use to see if a series or a sequence or an integral is convergent or divergent. So let's get started. It's a good idea to know ahead of time a few series that will always converge. Here's one series. If I have a constant to the k from 1 to infinity, that converges as long as that constant is somewhere between 0 and 1. All right, so c to the 1 plus c to the 2. That is an infinite geometric sequence, and if you treat it like an infinite series, then you can let a equal c and r equal c, and so the sum of that is c over 1 minus c, just using that formula that we've used before. So that series does converge. All right, similarly, any series of the form a to the negative k, where k goes from 1 to infinity, that converges as well as long as a is bigger than 1. Okay, it's basically the same series if you replace a to the negative 1 with c, since both of them are between 0 and 1. All right, so divergence. First, we want to be able to test for divergence. If every term in the sequence, if you have a sequence, and those terms, as I go off to infinity, if those terms do not approach 0 as k goes off to infinity, then obviously the sum of those terms will not converge to anything. So the sum will be divergent. Okay? For example, let's show that this is divergent. Well, this is a middle heavy expression. I've got k squared on the top and the bottom, and that's my highest exponent of k. So as k goes off to infinity, the limit will equal 2, which is basically the ratio of the lead coefficients. 2 on the top, 1 on the bottom. 2 divided by 1 is 2. So as k goes off to infinity, these terms approach 2. And remember, if you're adding terms together to get the sum of a series, and you keep on adding numbers that are getting closer and closer and closer to 2, well, that sum is not going to converge to anything. So that series, when you add them all up, is going to be divergent. Okay, this is not the only way you can show divergence, but it's probably the easiest one to try first. All right, now we have the comparison test. If I have two positive series, meaning that every term in the sequence is positive, meaning that every term in the series is positive, and if I know that every term ak is less than or equal to bk, then if the bigger series converges, then obviously the smaller one converges as well, and it converges to a smaller or equal number. Okay, but if the smaller one diverges, then the larger one must diverge as well. All right, so for example, let me show that 5 to the k plus 3 all to the negative 1. Let me show that that converges. All right, if I compare 5k plus 3 all to the negative 1 to just 5 to the negative k, then notice how 5 to the negative k is consistently, those terms are consistently higher than the terms in the sequence I was given. So what that means is I know that 5 to the negative k converges. We've talked about that. So that means that something that is consistently less than that will always converge. So if you can find a sequence or a series to compare the one you're given, and it converges, then the one that we're given is also going to converge. All right, so that's the comparison test. Then we have the limit comparison test. So if I have two sequences again, AK and BK, and I'm finding the sums of those sequences, I'm finding the series, then if I divide them, and AK over BK, so the ratio of each of the terms, and that gives me some limit, some L, that is bigger than 0, then if one of the series converges, then so does the other one. And if one of the series diverges, then so does the other one. All right, so for example, let me show that 7 to the k minus 2 all to the negative 1 converges. So that is a positive sequence, a positive series that converges, and so is 7 to the negative k. So if I divide those and take the limit as x goes to infinity, then I've got 7 to the k over 7 to the k minus 2 once I get rid of those negative exponents, and that converges to 1, which is bigger than 0. So 7 to the k minus 2 to the negative 1, that converges as well. Since 7 to the negative k converged, then the one I was given converged as well. Then I have the integral test. So if I have a positive decreasing function f of x, where x is greater than or equal to 1, then if the integral of f of x converges, then the sum of those individual terms in the series is also convergent. But if the integral is divergent, then the sum is also divergent. So, for example, if I wanted to show that the sum of the terms k to the negative 2 cosine k to the negative 1, if I wanted to show that converged, then I make that into an integral, and I get x to the negative 2 times the cosine of x to the negative 1, and I'm finding the integral from 1 to infinity. And remember, from my lesson on improper integrals, if I have infinity at the top, I can change that to a b and find the limit as b goes off to infinity. Well, fortunately, that function is one that I can find the antiderivative of, and that is the negative sign of x to the negative 1. And if I evaluate that at 1 and b, I will get negative sign of 1 over b plus the sign of 1. And if I let b go off to infinity, that's going to get the 1 over b is going to get really, really close to 0, meaning that the sign of something that gets closer and closer to 0 is also going to get closer and closer to 0, leaving me just with the sign of 1, whatever that happens to be. So since that is a number, the integral converges. That means that the series also converges. All right, and then I have the alternating series test. If I have an alternating series, meaning that the terms change sign with every term. So one term is positive, the next term is negative, the next term is positive, and so on. And it keeps changing sign. Well, let's say that the next term, the absolute value of the next term is always less than the absolute value of the term that came before it. And if the limit as k goes off to infinity, if those terms approach 0, then the series is convergent. So let's look at this example here. I want to show that the sum of negative 1 to the k plus 1 times k to the negative 1 converges. Well, the absolute value of the kth term is 1 over k. And the absolute value of the k plus first term is 1 over k plus 1. I know that then the next term is always going to be less than the previous term. So the terms are decreasing, and also the kth term does approach 0 as k goes off to infinity. So that means that the series does converge. All right. Now, there's approximation errors that I need to consider with an alternating series. So I have this sum, this infinite sum of an alternating series, such that it satisfies all of those conditions that I talked about in the previous slide. The error in taking the first n terms as an approximation to the actual sum is less than the absolute value of the next term. Okay, so the actual sum minus the nth partial sum will always be less than the n plus first term. Okay, obviously we need to look at an example of that because that's a lot of language to absorb. So how many terms of the sum I was just talking about are necessary to find an approximation that is accurate to within 1/1000th? Well, the absolute value of the k plus first term is going to be k plus 1 to the negative 2. And because the negative ones are meaningless once I'm taking the absolute value. So if there's a negative 1 there, I can just ignore it. That is going to be less than k to the negative 2, which is the kth term. So it does meet those requirements where the absolute value of the k plus first term has to be less than the absolute value of the kth term. Also, the limit as k goes off to infinity of the kth term, the absolute value of the kth term, that does equal 0. So the difference between the infinite sum and the nth partial sum is less than the n plus first term, which is n plus 1 to the negative 2. So I need to know when is that difference going to be less than 1/1000th, which is what I was asked in the question. So if I if I flip both of those fractions upside down, n plus 1 to the negative 2 will become n plus 1 to the 2, and 1/1000th will just become 1000. Then I square root that, and I subtract 1, and I get that n would have to equal 30.62. So basically, I need to go up to 30.62 terms. There is no 30.62 term, so I have to go to 31 terms in order for the partial sum to be within 1/1000th of the actual infinite sum. All right, then we have what's called the ratio test. If I have a series, and again, I take the absolute value of the ratio of the k plus 1 term divided by the term that comes before it, and if as k goes to infinity, that is less than 1, then the series is convergent. If it's bigger than 1, then the series is divergent. And if it equals 1, I can't really say one way or the other. So that test is inconclusive and I need to find another test. So I'm going to try and show that the series 2 to the k over k factorial is convergent. So I'm going to look at the absolute value of the k plus 1 term divided by the k term, and there they are there. I basically, instead of dividing by the k term, I multiplied by the reciprocal of the k term. So that's why I get k factorial over 2 to the k. So let's simplify that. 2 to the k plus 1 is just 2 times 2 to the k. And k plus 1 factorial is just k plus 1 times k factorial. And I do that so that I can cross stuff out. The k factorials will cross out, the 2 to the k's will cross out, and I will get 2 over k plus 1. That equals 0 as k goes off to infinity. That is less than 1, so 2 to the k over k factorial is convergent. Now I need to talk lastly about absolute versus conditional convergence. If I have a series and I want to know if it's convergent, well, if I know that the absolute value of that series is convergent, then the series itself is absolutely convergent. Okay, so I'm going to show that this series is absolutely convergent. All right. Or actually, that is one that I talked about because the absolute value of that is convergent. So the series itself is absolutely convergent. If a series is convergent but the absolute value is divergent, then the series is conditionally convergent. So for example, the series negative 1 to the k plus 1 times k to the negative 1, that is conditionally convergent because the series itself is convergent, but if I take the absolute value of all of those terms, that negative 1 thing goes away, and I just end up with k to the negative 1. That's not convergent, that is divergent. So this series is conditionally convergent. All right, so that is a lot of information to absorb. I know you will have questions, and if you do, please feel free to ask me those questions, and I will see you tomorrow.